Well, hello, everyone. Chemistry 1001. We are into Chapter 8, Acids and Bases. Very important section. Do remember, if I covered it in class, you would be responsible for that. And this new material, which will be defined in a study guide. The study guide will just be from the new material. You have the 4 past study guides to help you with the final. More information on in class. Let's switch over to our laser pointer. We just have here where we have an acid solution, and you see H3O, which is hydronium cation floating around. And then you see hydroxide over here, OH with base. And that is part of the definition of an acid and a base. So make sure that makes sense to you. We'll see how protons are added to water to make it the hydronium cation, which often is abbreviated as H+. Why can we do this with water? Why can we simply add a proton to the water structure and make it an acid and it becomes hydronium cation, H3O? That's because, well, part of it is that water is amphiprotic. It can not only accept a proton, it can donate a proton. And so we're going to see how that works here. Water is the most common solvent for acids and bases. It's usually dissolved in acids and bases. Solute-solvent interaction between water and both acids and bases are what basically acid and bases, of course, are soluble, especially mineral acids versus a large molecule like an organic acid. And we haven't even discussed that, but these positive and negatively charged metals that we've looked at in polyatomic anions and things like chloride and fluoride, which are negatively charged, are all very soluble in water because they're polar. They have a negative charge, and water sort of has a partial positive and not sort of, it does, has a partial positive and a partial negative charge. Remember what I talked about earlier in the class this year. So conjugate acids and bases. So now we do have a fairly good understanding of what an acid and a base is from our past discussions. If you don't understand that, please review this. But acids and bases, for example, we can have this rather generic reaction, and we have an acid which has a proton to donate. And then we have the rest of the molecule, which is A. So that stands for HA as an acid in the proton. This is actually a weak acid because the arrow goes in 2 directions. Don't confuse molarity with strength of acid. You can have low molarity and have a low molarity and still have a very strong acid, HCl, whether it's 0.02 moles or 2 moles of HCl. It's still considered a strong acid, not because of the concentration, but because of the chemical behavior of that acid. What I'm displaying in front of you here is a weak acid. So let me just write, this is weak. Not because of concentration, but because of how the double arrow represents that it does not disassociate completely. You have reactants and products and reactants. We would need some kind of equilibrium constant to figure out which side dominates, which side is more concentration, the reactants or the product side. But the products have special names that we haven't talked about, and they can be called conjugate acids and conjugate bases. And every weak acid or weak base is going to have a conjugate acid and a conjugate base. In this case, we can see that this is the acid and this is the base. And then we have now the weak acid has its conjugate base, which is A minus. And the base has its weak or its conjugate acid. So the opposite, a weak acid is going to form a conjugate base. A weak base or a base is going to form a conjugate acid. So they're linked together. They're pairs. this is a good graph to kind of just reiterate what I just mentioned. And um, here we have obviously, what is this? Just looking at the arrow tells us the arrow goes two directions. Do we have a weak acid or a weak base? Or excuse me, do we have a weak acid or a strong acid, or a weak base or a strong base? Well, because the arrow goes in two directions, it must be either a weak acid or a weak base, because it doesn't ionize completely. Has nothing to do with the concentration, has nothing to do with the molarity when we say strong acid or weak acid, or strong base or weak base. But conjugate acid pairs, if we have an acid, what's left over after it donates its proton is the conjugate base. If we have a base, what's left over after the base accepts the proton is a conjugate acid. Now, I'm not going to get too much into strength. That's more of a general chemistry 2 question. But conjugate acids is what the base becomes after it accepts a proton. And a conjugate base is what the acid becomes after it donates a proton. So go ahead and look that over, make sure it makes sense. So yes, looking at this again now, so we're just understanding there's conjugate acid base pairs. So the HY and the Y, it's the conjugate acid and the base, and then we have the acid and the conjugate base. So we need to make sure we understand those pairs and which is which. The conjugate acid and conjugate base are usually on the product side. So conjugate acid and conjugate base are over here on the product side. The acid and the base is usually represented on the reactant side. Strength, as I mentioned, it's not a measure of concentration. Yes, that has something to do with how powerful the acid is or how weak the acid is, but a strong acid or a strong base or a weak acid or a weak base has nothing to do with the concentration per se directly with these terminologies. We tend to, we would say a concentrated acid or a concentrated base. A strong acid or a strong base doesn't give us any numbers to tell us just how many protons are there, or how many, if we have a strong base, or how many hydroxide anions are there. We don't know. So strong acids, these are a list of them. You should probably memorize them. When it's a strong acid, you have an arrow that goes in one direction. The arrow only goes in one direction. It completely ionizes. There's no double arrow. There's no equilibrium. There's simply, and this happens when it responds like this when you throw it in water. You have to throw it in an aqueous solution, and then it will ionize completely. And so HCl, which is hydrochloric acid, HBr, which is hydrobromic acid, HI, which is hydroiodic acid, HNO3, nitric acid, H2SO4, sulfuric acid, and HClO4 is perchloric acid. Those are all strong. They completely ionize. The arrow only goes this one direction, as you see here. Strong base, it's the same thing. In water, a strong base only ionizes in one direction. It does not return to the reactants. It simply ionizes completely and disassociates completely with its cationic pair in water in aqueous solution. There's also some metal hydroxides. Remember, when metals react with oxygen, they form bases. Metal hydroxides are quite common, and they need to react with acids to be redissolved. Weak acids, as we mentioned, these are just a couple of examples. What we saw previously was strong electrolytes. A strong acid and a strong base are both strong electrolytes, not something we want to drink. They're not the only type of electrolytes. For example, potassium is an electrolyte, but we really don't want to drink potassium hydroxide, and we don't want to drink hydrochloric acid. So be careful. Electrolytes is a broad range of charged particles, negative or positively charged. Weak acid, and they conduct electricity. Now, weak acids, not so much. They're weak, so their arrow goes both directions, meaning you have an equilibrium, meaning you have some reactants on one side and you have some products. You have some reactants on this side, and you have some products on the other side. And all four of these species are present at equilibrium, where with strong acids, only the deionized proton and the anion are present, and usually the proton is picked up by the water. And that's what we see here. Although we do have this equilibrium, water accepts this proton and it becomes H3O, and it can go backwards. Water can donate the proton, which is what makes water amphiphilic. It can do both. It can be an acid, it can be a base. The same thing happens with carbonic acid. We have this can donate the one proton initially, and it becomes H3O plus, which is the same as a proton, which is acid. And you have this acid that turns into a conjugate base, and this can accept a proton from the hydronium cation. So make sure you kind of understand the pairs. Here's some examples of weak bases. What is a base? It can accept a proton. So water being capable of acting like an acid and water acting like a base. Here, water will be turned into a base in much lower concentration than the water, of course, but ammonium will come over here and take a proton here and break the hydrogen off of water and make a hydroxide anion, right? So there are lone pairs on nitrogen, and it comes over here and attacks one of the hydrogens, and then we create the hydroxide anion, which is the definition of a base. But this is a weak base because the arrow means that it goes to products and products go to reactants. So the reaction goes back and forth, never to completion, as a strong base would go to completion, like sodium hydroxide. Pyridine, we don't really need to worry too much about the structure, except for that we have this nitrogen that can go over here and accept a proton from water and generate a hydroxide, and then a hydroxide, which there's lone pairs on hydroxide. It can, since it's a weak base, it can go over here and take one of these protons, and the reaction can go this way as well. The reverse or the forward reaction is possible. These are weak bases. They do not ionize completely. Aniline does the same thing, the same properties, just a little bit different structure. Aniline and pyridine are differ by one carbon, and it can go over here and take a hydrogen and thereby produce a hydroxide, and the hydroxide with its lone pairs can come over and take a hydrogen. And so the reaction goes back and forth as we would expect, as weak bases and weak acids do. So again, what we see here is a strong acid, right? It's a strong acid because it disassociates 100% in water. The arrow goes one direction. It does not reassociate with its hydrogen. It gives it up completely, and it never returns in this manner at all in a solution. So we call this a strong acid, which has nothing to do with the concentration. We could have 0.1 molar of hydrochloric acid, which is 0.1 moles per liter, or we could have 5 molars of hydrochloric acid, which is 5 moles per liter. And it's still considered a strong acid, yet it can be less or more concentrated. And a weak acid, we just got done looking at those weak acids and weak bases. They have a dual arrow, and it does not disassociate 100%. We have these acids, and then we have the conjugate base. Once the proton is lost, we see the conjugate base. Once the proton is lost, we see the conjugate base, and so on. And some of these are strong acids, and some of these are weak acids. Some are what they call a diprotic, where they give away 2 hydrogens, such as sulfuric acid. And it's not the only one, but an important one. We have H3PO4, which is a triprotic acid. It gives away 3 protons. So, and sometimes the first proton will be a strong acid and the other 2 will be weak acids, meaning they don't ionize completely. When they're weak bases or weak acids, and we're talking about weak acids. So we can look at this and we can kind of compare things here. we can say, which is stronger, which is weaker. I don't want to do too much of that, but we know that, which acid is stronger. Well, this thing's protonated, this hydrocyano group, this protonated cyano group, versus this HF. Well, we know HF is a weak acid, but it's stronger than HCN, and we can determine that with values and numbers. And then we can look at which base is stronger, the cyanide or just simply water, and the cyanide anion, cyanoanion is actually stronger. You would need more assistance to help you understand this. We do have numbers that can measure this. We're not that far along where we need to do that, but we will eventually. If you take more chemistry, you'll learn this more thoroughly. Now, identifying conjugate acid and base pair. So all of these, okay, we know that with a strong acid, the arrow is just going to go one direction. But if we have a weak acid, we're going to have the arrow going both directions. And this here, if this is a weak acid, this hydrogen sulfide is a weak acid. And then we have this weak base. We know that the arrow goes both ways. So only one of these arrows goes just to one direction, which is the strong acid. We've said nothing about the concentration. We're able to determine what it means to be a weak acid and a weak base, or a strong acid or a strong base. And we know that this is always going to interact with water molecules. So if dissolved in water, it will come over here and take that proton, and you will end up generating H3O+. That's the hydronium cation, and then you will generate the anion, which is the conjugate base. The hydronium cation that you produce is a conjugate acid. Okay. The water acted as the base, so the water is the base, and HF, or hydrofluoric acid, is of course the acid. But then you link these pairs together. Fluoride comes over here, so we have the acid conjugate base, and here we have the base and conjugate acid. Sometimes, let's take a look at what the base does. Remember, a base accepts a proton, and it can do that from water or hydronium, but let's just assume this is water, and it can come over here and take one of the hydrides and then protonate this. This ammonium group gets protonated, so we have NH3 instead of NH2, and that is now positively charged. And then we have hydroxide anion formed with a negative charge. So the water acts as the acid, and the hydroxide is the conjugate base. And this amine group here, this primary amine group, acts as the base and then becomes the conjugate acid, where and we're not really even looking at the difference, should I say, powers of these acids and bases. So the degree of dissociation defines a weak and strong base. Concentration also is effective in telling us something about what kind of acid we got. For example, it's still true that if we had 5 molar HCl and only 0.5 molar HCl, that there would be more acid and more protons that would be donated from the 5 molar more concentrated solution. But strong and weak is something else in chemistry. It talks about whether we have an equilibrium, which we always do in a weak or a weak acid or a weak base. But if we have a strong base or a strong acid, there is no equilibrium. The reaction goes one direction, and that's to completion, to products. So thank you for listening. We'll be back with more materials from Chapter 8. Take care.